Okay, let's continue. The last equation, some moment, okay, will be used to calculate this bending moment mb. Right, so some moment, well, about what point? You can choose any point, okay? But a convenient point, well, maybe point B. Okay? And doing that, then this VB would disappear in this equation, right? So you only have to consider this 1,000 Newton and MB, obviously. So let's say I'm going to do counterclockwise positive, right? Since I assume this MB to be counterclockwise direction. So I have MB positive, right? And a moment from this force, 5,000 Newton force, and this force tends to create a clockwise direction, which is opposite to my positive direction, so it's negative. Okay. 5,000 Newton times moment arm, which is the length of AB, which is 3 meters. So 3 equals 0. Therefore, MB equals, move this over, positive 15,000 Newton meter, okay, or 15 kilo Newton meter. Okay. That's positive, means my originally assumed direction of counterclockwise is correct. Okay, so I can redraw this now. Draw a second picture of AB with the correct forces and moment direction. Right? So I have 5,000 Newton, and I don't have normal force now. I only have a shear force going down because this negative number right there. So this shear force is 5,000, and I have a bending moment. Okay, in the counterclockwise direction, 15,000 Newton meters. That's all. So this is your free body diagram. Okay, everything has been calculated. Okay. So this is an equilibrium. Now notice that in this analysis, this applied couple moment of 9,000 Newton meters does not appear here at all. We don't take into consideration of this, okay, for this calculation. Okay? And that is because this 5,000 Newton force, okay, this reaction force at A, the fact that it's 5,000 is because we have already taken into consideration of this couple moment right here. Okay? In this calculation, in looking at this free body diagram, the whole thing, right, in figuring it out at A, I have used this 9,000. I've taken into consideration. Okay? So the effect of this 9,000 Newton meter of couple moment have resulted in a reaction force of 5,000 Newton at A. Okay? So that's why this couple moment doesn't appear here at all. Okay? Otherwise, you would have double counted the effects of this couple moment, right? So it doesn't appear here at all. Okay? So what you do here is just draw whatever that you see, okay, in this picture. Okay? This section AB. Right? This is reaction force, and then you have these 3 internal forces and moment. Okay, so now section AB is done. Okay, so I now know exactly what's going on at B. Right, so we have this shear force of 5,000 newtons going down, and I have a bending moment of 15,000 newton meters going counterclockwise at B. Let's move on to C. What's going on at C? Since B and C are really close to each other, okay? They're really right next to each other, okay? close to this line right here, with the 6,000 Newton forces applied, right? Since they're so close to each other, you might expect that, hey, they might be quite close to what you calculated here, right, at B. Well, let's look at it. Go through the same calculation, exactly the same thing. Okay? Except now, you draw a free body diagram for a C section. Okay? Now, since AB and AC, they're almost the same length. Now, B and C, they're really close to each other. So the length AC, I'm going to take it as 3 meters as well. Okay? Just like AB. Right? So it's 3 meters. Except now, for the free body diagram, I have, well, same as this AB, I have 5,000 newtons going up. For this AC section now, I have to take into consideration the 6,000 newtons, because C is just to the right of it. So 6,000 newtons actually appears here in this free body diagram, where it doesn't appear here in this AB diagram, right? Because it's outside of this free body diagram, this section right here. So 6,000 newtons now is included in this section AC. And what else? Well, you have these 3 unknown internal forces. So I'm going to assume the same direction as the other section, right? So this is my normal force at C. I have shear force at C, and I have bending moment at C. Same deal. 3 unknowns, 3 equations, shouldn't be a problem. So let's go through the calculation. Some forces X equals 0 first. For this whole free body diagram, immediately you should see this normal force is 0. Okay? So again, there's no normal or axial forces internally. Next, apply sum of forces vertically. I have positive of 5,000 newtons, this, and I have negative of 6,000 newtons coming down, so negative, and I have shear force. That's it. So 3 vertical forces in the y direction. Okay? So, crunch numbers. Bring that over, so 6,000 minus 5,000, so it turns out it's 1,000. Positive. Positive means my assumed direction is correct. Okay? It actually points up now. Okay, last equation. Sum of moment. About what point? Well, a convenient point to sum moment about is point C. So I have, well, let's see, I'm going to again assume that counterclockwise is positive. So I have this bending moment, MC, and a moment due to this force, and that's clockwise, so it's negative 5,000 times moment arm of 3 meters. And that's it. So these other forces don't have moment about C because they pass through C. So 0. Therefore, this bending moment C equals 15,000 newtons. Positive. Positive means this direction of counterclockwise is correct also. Okay, that's it. So now I've calculated the internal forces at the C point. Okay? Let's compare the two, B and C. Now B and C are really close to each other, but the shear force at B is 5,000 newtons going down. Okay? Whereas for AC, okay, let's draw a little bit, let's make some room. Let's draw AC. Okay? I can draw really essentially the same length. Okay? I have 5,000 here, and I have 6,000 applied force. I have this shear force of 1,000 going up this way. And I have a bending moment of 15,000. Okay, so compare the two. Okay. So internal forces, right? I have 5,000 going downward at B, but at C I only have 1,000 newtons, like it's going up. Okay, big difference, right? 1,000 down, 1,000 up. But as far as the bending moment goes, both have the same. Okay, so 15,000 newton meters counterclockwise. This is also 15,000 meters counterclockwise. That's all. Okay, so this calculation really is quite straightforward. You apply the exact equation that you've known for so long now. Okay, the math is really very, very straightforward. It's all algebraic equations. Right? And the key here is setting up your problem, choosing the right free body diagram, the right section, okay, and drawing the right forces and moment, okay, and then apply the equation to your free body diagram, and you'll be okay.